Hello everyone, welcome to my presentation. My name is Dustin Lowe. I am an undergraduate chemistry major at Coastal Carolina University, and I will be walking you through my research into the synthesis of a benzyl substituted phydianidine. Let's just jump right in. We'll start with a relatively important question. What is phydianidine? Now, phydianidines are a class of marine compounds isolated from the mollusk Phydiana militaris. Natural products have long been a source of pharmaceutical advancement, and this compound is no exception. Phydianidine contains the first natural occurrence of a 1,2,4-oxidiazolyl ring moiety, shown here in yellow, in a marine product. It has two naturally occurring compounds, A and B, in which the only difference is the occurrence of a bromide on the indole in A, represented here as an X. Phydianidine-based derivatives have proven effective in neuroprotective studies against such agents as amyloid beta 2535 peptide, hydrogen peroxide, and oxygen glucose deprivation. Given that, we decided we wanted to look closer into this molecule and what we could do to further our knowledge of its properties. We decided to keep the indole on the end and substitute other heterocycles in place of the 1,2,4-oxidiazolyl ring in order to gauge its importance in biological activity. So a number of these substitutions have been done before, necessitating that we branch out a bit. Most groups before us focused on the modification of this terminal guanidine chain. I'm underlining here. So we decided to focus on the oxidiazole in the middle. Now, my focus was substituting the oxidiazole with a simple benzene ring, shown here in yellow. Then the molecule was further changed with the additions of a furan, another benzene, and an ethyl ether in place of the long alkyl guanidine chain. So this change was shown by Zhang and co-workers to make these compounds neuroprotective against oxidative damage. We pursued compounds bearing this side chain so we could determine how changes to the central ring would impact this activity. So now comes somewhat of the hard part, figuring out how to construct this molecule. Eventually, we decided to start in the middle and work our way out. To begin, I'm going to walk you through a few key parts of the synthesis. I started in the middle, like I said, branched out from there, starting with a halogenated furan ring and using a Suzuki reaction in the conditions under the arrow. I created the compound you see on the top right. At this point, it became apparent that because it worked well the first time, we would just do it again. So I halogenated the furan ring using simple bromine and dichloromethane, and using the same Suzuki mechanism to add the other heterocycle. Now, the Suzuki reaction is very useful here because the boronic acids that I used to build this molecule up to this point are easy to attain and result in decent yields, not to mention that a lot of the reactants and catalysts I needed were already on hand, so I could just jump right in. Now, at this point, I have the furan ring flanked on either side by a benzene. The next step was to figure out how to attach the indole. Basic Friedel-Crafts acylation would do here very nicely. First, however, the ester on top of the molecule had to be saponified by the use of trimethyltin hydroxide to produce this carboxylic acid. Only a few more steps now. I was able to turn the carboxylic acid on the top left into an acid chloride using oxalochloride and DMSO. Now, at this point, I was finally ready to use the Friedel-Crafts acylation that I mentioned a minute ago. Aluminum trichloride and the indole were the last things I needed to add onto the molecule. Now is when we get, unfortunately, into a bit more of a speculative realm, as we have yet to verify the results of the indole addition. That will be done at the beginning of the next semester. Following that, the final step, as you can see, would be the reduction of the ketone group between the benzene and the newly added indole molecule. All right, going into this next semester, the initial task, as I mentioned before, will be verifying the results of the indole addition, followed by the subsequent reduction of the ketone. Now, after that, we will try to optimize the yield of the indole addition, a reaction that in the past has been proven to be somewhat unreliable. Additionally, all reactions will be improved and optimized as much as possible. So when this process is made more efficient and the product can be reliably synthesized, it will be passed off to another team on campus who can measure the biological activity in a controlled setting. Now, I wanted to finish by thanking the SC INBRE program and CCU for allowing me this opportunity, and thank you all for listening.